My name is Ben Weiss. I'm an engineer on the Android Developer Relations team. I'm joined by Lokesh Gidra from the Android Runtime team. This is what's new in app performance. We'll start up with new developments in performance tooling, then talk about tools and metrics to improve and monitor app startup. And this will include the fastest way to speed up your code execution, baseline profiles. Then I'll introduce you to tools and libraries for jank avoidance and monitoring, before handing it off to Lokesh. He will take you through exciting improvements in the Android framework that provide every app from Android 12 onwards with performance boost. Let's take a quick look at the available tools that will help you when dealing with performance issues within your apps. Firstly, you can investigate directly from the comfort of your IDE. Android Studio offers a variety of profilers that help you better understand how your app is doing. Open the Profiler tab during a debugging session and load a trace file to get detailed insights into your app's CPU, memory, network, and energy usage. You can export results of your profiling session and share it with your team. And even if you don't have Android Studio installed, you can look at the resulting data using Perfetto. Perfetto is a web-based application that you can use to navigate through app traces. With Perfetto, you can dig into detailed information about many aspects of your app, as well as the underlying device state at any given time. You can use it to analyze and explore app traces in detail, profile the entire device of your app is running on, and use the trace processor's SQL-based interface for detailed analysis, attach exported data to bug reports, and more. Android Studio profilers and Perfetto traces are interoperable, so traces that you have exported from Android Studio or an Android device can be analyzed in Perfetto as well. In most cases, your users won't be able to share detailed traces with you if something goes wrong. We provide another tool that helps you monitor how your app is doing out there. Android Vitals. Android Vitals are part of the Google Play console. You can use it to help understand and improve your app's performance on real devices. You can see how your app is doing and compare data to other apps. And thanks to continuous monitoring, you're able to see information on what's going on and get notified when anomalies occur. Android Studio, Perfetto, and Android Vitals offer deep insights into your app's performance. These tools are able to provide the data you need to decide where to start improving your app's performance. Now that I've introduced you to these tools, let's talk about a common performance issue: app startup. This is where you can make a good first impression on your user or leave a not so good one, but that's not what we're here for. Android considers 3 startup states: cold, warm, and hot, which build up on one another. During a cold start, firstly, the app's process will be created. Content providers are initialized before your application's onCreate method gets called. Having many content providers can slow down your app start unnecessarily, and I'll show you a way to avoid that later. Then your application onCreate will be called, and the next stages of the app startup kick in. If a cold start takes more than 5 seconds, Android Vitals will consider this excessive. Users are likely harsher than that. A warm start begins when your activity's onCreate method gets called. During this phase, the app process is already running, and the current activity gets created or recreated. This is where resource and layout inflation for that activity happens. Android Vitals considers warm starts over 2 seconds excessive. A hot start begins with a call to activity's onStart method. Hot starts happen when only an activity needs to be restarted, such as when it's being brought back from the launcher after briefly leaving the app. This is where your first draw pass happens. It includes measuring, layout, and rendering of the view hierarchy, and hot starts should be faster than 1.5 seconds. Each app start can be measured in 1 to 2 end states. The first and the faster one is time to initial display, or TTID for short, which means that your app has launched, objects and dependencies have been initialized, and the launcher activity has been created. The first frame of your app has also been drawn. The second metric is time to full display, or TTFD. At this point, all relevant data in your app has loaded, and the point of display has already passed. The user can now start interacting with the loaded content of your application. Because each app is usable from a different moment on, Android can only tell you when your app is initially displayed, and you have to let the framework know when your app is usable by calling activity's report fully drawn method. You can use this for gathering startup metrics, but it also provides the Android framework with information about code paths that should be optimized through the ahead of time or just-in-time compilers. And you can easily spot both states in Lockhead by filtering for displayed or fully drawn. But can't you just ignore all this data and continue developing features? We worked with several partners to find out whether focusing on app startup performance is worth it. The team behind Google Maps for Android improved the app's startup time by 30% after introducing baseline profiles, a new way to improve app launch and hot code path performance. This startup improvement led to an increase in searches of 2.4%. I'll show you how to use baseline profiles in your app later in this session. The team behind the short video app, Josh, uses Android Vitals as a powerful source for app performance metrics and a part of the Google Play console to see how their app is doing with real users. The investment in startup performance led to an average reduction in 30% of app startup time, and it paid off. According to Josh, more than 1 million active users were retained thanks to the improvements. The engineering team profiled app startup sequences and analyzed traces with Android Studio profilers and Perfetto. Code was moved out of critical startup path, and the improvements were verified and are now monitored using the macro benchmark library. Zomato, a restaurant aggregator and food delivery app, serves customers in more than 500 cities in India alone. The app has more than 43 million active users with more than 1.5 million orders per day. Zomato also was able to improve their app startup time by an average of 30%. According to Zomato, this led to a 90% increase in day one user retention and an increase in orders of more than 600,000. To achieve this, the engineering team removed unused libraries, introduced the app startup library, lazy loaded code where possible, and overhauled the layout and view strategy. You've seen that shaving off time from app startup has a direct and positive impact on user behavior, which in turn improves business metrics for each of these apps. And looking at this data, you should probably also invest some time in making your app launch faster. To help you better understand how well you're doing when it comes to app start and user flow performance, we created the Macro Benchmark library. The Macro Benchmark library enables you to gain data on app startup, frame timing, and more. You can monitor big picture performance by stepping through entire flows of your app using familiar integration testing APIs. You can run macro benchmark tests one-off or continuously on your integration server and decide whether you want to run tests in a cold, warm, or hot startup state. To get started adding macro benchmarking to your project, open the new module dialog. Select Benchmark and Continue. Here, select Macro Benchmark, modify the module and package name to your needs, and click Finish. Android Studio will take care of creating the benchmark module, modifying your build script, and adding the right dependencies to the benchmark build time. This build type will build up on the release build type to keep performance close to your production app. But benchmark builds should not be obfuscated, so we recommend creating a separate ProGuard rule which contains Don't Obfuscate. The newly added module comes with a basic test that cold launches your application 5 times in a row. Instead of the launcher activity, which is the default behavior, you can create any intent your app reacts to and drive the test using UI Automator. This way, you can run entire user journeys. When I run this on a connected device, I see the results come in after the application has been created and torn down 5 times. I can also click on the results to analyze them more in depth in the profiler directly to identify performance bottlenecks. For more benchmarks and details, check out the performance samples on GitHub, linked in the description. Now let me show you an extremely reliable and quick to implement way that you can speed up your app's startup performance. Baseline profiles. Baseline profiles give developers a tool to guide Android's ahead-of-time compilation by providing a list of classes and methods which are used by the Android runtime to precompile critical paths to machine code. This can have dramatic effects on improving your app's startup speed and reducing janky frames. When a baseline profile is created, you can cover critical user journeys to make the path run super smooth from the first time the app launches. Library developers can also provide a baseline profile for time-sensitive code. This in turn helps apps to run smoothly when these code paths are accessed. The ahead-of-time compiler uses data provided from the baseline profile, so app instantiation and layout inflation are ready to go, and you don't need to wait for the just-in-time compiler to finish. More than 5,000 apps on the Google Play Store are already using baseline profiles in production. And with baseline profiles having approach stability, every app should start using it. Also, Jetpack Compose is one of the libraries using baseline profiles to reduce the time it takes an application to render composables. I'll now show you how to create your first baseline profile. This is a 2-step process. First, the baseline profile must be generated with a specialized macro benchmark test. This profile is then pulled from the device and placed in your application's source folder. In a second step, the profile installer picks up the baseline profile and installs it on the device during the app installation. The macro benchmark sample on GitHub also hosts this trivial baseline profile generator class. It uses the baseline profile rule to generate a baseline profile from the app under test, which is passed in using the package name parameter. This generator only starts the launcher activity and then waits for the device to be idle. But you could also start scrolling through a list or click on your primary call to action to provide a more complete picture of what users are doing immediately after the app has launched. When the profile is ready, you can quickly pull it from the emulator and put it into the main source folder alongside the Android manifest. We have seen huge performance improvements from real-world apps that are using baseline profiles and recommend you to ship one as well. Baseline profiles are very likely the fastest way to positively impact your app's startup time and frame rate. Next to profile-guided optimization, we also created the Jetpack App Startup Library, which helps you to avoid resource contention during app startup. It improves performance and component initialization by removing the need to use expensive content providers during app startup. Work Manager is one of the libraries that uses the startup library underneath the hood. So if you're using Work Manager, App Startup already does speed up your app launch. To use App Startup, add the library to your dependencies, then implement an initializer like this one for each of your startup critical components. The create method returns the instantiated object of your target class. And you can also provide a list of dependencies which need to be instantiated before the target class is ready. This way you can provide structure to the initialization sequence, which was not possible with content providers. Next to startup improvements, ensuring that an app's UI runs smoothly and without skipping or dropping frames is a big part of improving performance. The term jank is used to describe this problem. Jank occurs when your app does too much work on the main thread, which leads to missing the timing window for drawing the next frame. In extreme cases, this can even lead to your entire activity not responding and the dreaded ANR dialog. During our work with external partners, we've seen how focusing on performance and removing jank has impacted their apps. The social media platform ShareChat has over 180 million users with more than 2.5 billion monthly shares. ShareChat was able to remove almost half of dropped frames, which is a huge gain for usability. This smoother app experience led to an increase in app usage of about 10%. To achieve this, ShareChat firstly profiled and benchmarked their app to learn about areas to improve. Using this data, the engineering team then optimized the layout code, moved heavy tasks off the main thread, and migrated to Kotlin coroutines. Jio, a large Indian telecommunication company, has an Android app with about 500 million installations. This makes it one of the most widely used apps in India. Using Android Vitals and Firebase Crashlytics as guides, engineers at Jio were able to improve their app startup time by an average of 35% and decrease their unresponsive rate by about 40%, amongst other improvements. Jio attributed the 20% increase in ratings, 5% drop in uninstallations, and overall drop in negative user feedback to these changes. OKCredit, a bookkeeping app for small businesses, used Android Studio profilers, benchmarks, and Android Vitals to identify areas to improve performance in their app. OKCredit was able to reduce the rate at which their app became unresponsive by 50%. The engineering team moved code out of hot paths, avoided unnecessary operations on the main thread, and they also reduced image file size and worked to optimize layout inflation using ViewStub and Async Layout Inflator. According to OKCredit, this led to an increase in user retention of more than 20% and an increase in transaction of 30%. Again, we see that focusing on performance can have a very direct and significant impact on your user experience and business metrics. Android Studio, Vitals, and Firebase Crashlytics are great data sources for real-world user data, and made it easier for you to investigate and monitor jank both during development and production. Android Studio already offered a powerful suite of profiling tools that help you gain insights into various states of your application. With the release of Android Studio Dolphin, we made it even easier to detect when jank occurs by adding a jank detection track to the CPU profiler. I'm using a sample that causes jank when scrolling through a recycler view on an emulator with API 31. In the Profiler tab, I click on the CPU profiler swim lane. Jank can be detected when collecting the system trace, which I select here and then click record. Now scrolling around in the sample app will produce traces, which I can look at in a moment. After I click stop, the traces are downloaded from the device and parsed directly into the profiler. The system trace recording contains a lane which highlights every janky frame. By clicking on a single one, I can see exactly what happened and what kind of jank occurred. Sometimes reproducing janky frames can be challenging. The device's load state can change quickly and your timing results will likely vary. That's where the Jetpack micro-benchmarking library can help. With this library, you can test frequently run code over and over again until you have statistically significant data. Our developer guidance that's linked in the description below shows you how you can obtain consistent results. The micro-benchmark library is perfectly suited for hot paths, which can become a source of jank. With the library, you can verify whether the performance anomaly you've seen from vitals or in your profiling is just a fluke or an actual cause for concern. The Microbenchmarking 1.1.0 release provides several new features. Allocating memory can be a performance concern, especially on older platform versions. The library introduced a new profiling stage which counts allocations and prints them in the test results. We also introduced profiling support. With this, you can load traces in Android Studio for further inspection after the benchmark is done. The detail of tracing is configurable in your build script. This provides you with more detailed information about the results of your benchmark run. We also made the setup faster. Instead of a manual setup process, you can now use Android Studio to set up macro benchmarks. Again, the new module dialog is here to make setup a bliss. Select benchmark, then micro benchmark. Adjust the module and package name to your preferences and click Finish. This template will create everything you need to get started with writing your own micro benchmarks and even a basic example. You can write your own benchmark tests the same way you write any other instrumentation test and access your app's resources and classes from within library modules. Then, to run the micro benchmark, attach a test device and hit Run. When your test is finished, you can see and profile the results directly in Android Studio. But sometimes it can be hard to reproduce Jank locally. Using a device which might be currently throttled or underpowered for the task at hand is not always possible. And this is why we created an API to help you log and track Jank, where it happens, on your users' devices. JankStats is a lightweight library which offers compatibility down to API level 16, and where better to optimize than on slower devices running lower API versions. JankStats enables you to identify, attribute, and report frames as they happen. You can get a frame data from real-world devices, identified through heuristics within the library, and then you can add more context by logging how the user got into the janky frames. JankStats monitors every frame and enables you to aggregate this data. You can decide to upload and analyze it later on, similar to other logs. To use JankStats, you first create a listener within your activity and attach it to your app's window. This enables reading data for every frame, and with that you're tapped in to read data for every frame that your app produces. You also can check whether the frame in question is considered janky, and add further context before adding the log data to your reporting queue. As this can be logging many frames, this listener has the potential to create a lot of data for you. So instead of logging everything and sending the reported data off immediately, you should aggregate it locally and send it together with your other reporting data. And keep in mind that operations you're doing in this listener run very frequently, so keep them as lightweight as possible. To provide meaningful metadata, use the metrics holder attached to the view hierarchy. Here you can add data that is relevant to your app as key value pair. For example, in a nav controller, you can write the navigation destination to the performance metrics holder. You could also provide information like scroll state of a view. Now, when a jank is detected, the frame data being reported will have all the information you need to reproduce the problem. We continue to make it easier for developers to improve app and performance by bringing guidance and best practices in one place. Soon, also our developer documentation on performance will be more helpful than ever. You'll hear more about this in the coming month. You have now learned about new tools and libraries that you can use to improve and monitor apps and libraries. I have shown you that focusing on app performance, in particular app startup and jank avoidance, has clear benefits for your app and business. And we continue to improve the performance of the Android framework as well, so you get to see app performance improving without having to actively work for it. Lokesh from the Android Runtime team is here to give you the rundown of under-the-hood performance improvements.
Thanks a lot, Ben. Now it is time to show you new features in the Android framework to keep your app performing at its best. Let's start with the biggest news about Art. Since Android 10, we have been modularizing system components. Now, many components can be independently updated through the Google Play Store. This means you'll be able to get new features of Android without having to wait for a system update to be available. We call this Project Mainline. In Android 12, Art also became a mainline module. This means that any device running Android 12 and above will get Art updates outside the Android release cycle, and runtime improvements will be mostly backwards compatible. This has enormous potential because it enables us to make new OpenJDK APIs available on old Android releases. This means that newer versions of apps which use advanced OpenJDK API will be able to keep their min SDK at Android 12 for much longer. Similarly, All the amazing performance improvements that we continue to make in Art will be available down to Android 12. In the following slides, I'm going to highlight some of the performance improvements that next Art module updates will contain. And of course, it also means that now Android devices will have longer-term support for runtime bug fixes. Just imagine, several years down the line, improvements made at that time in Art will continue to be available from Android 12 onwards, keeping your app performing well. How cool is that? Let's come back from the future sounds to features that improve your app's performance right now. Starting with the new garbage collector, which gets rid of fixed memory overhead. Like any other software platform, Android also has to strive under certain constraints. For instance, we know that most of the Android devices are battery driven, and in order to minimize the user trouble of charging the device repeatedly, we want its battery to last longer. Also, as Ben talked about it earlier, these devices are very user interface centric, and therefore we want the user to have buttery smooth experience when using these devices, and therefore cannot tolerate janks. And finally, something that doesn't impact the user but is critical to Android is the fact that the amount of cumulative memory committed to apps in terms of heaps, caches, etc. is almost always higher than the RAM size. If we aren't careful about memory usage, then the OS is forced to kill apps, leading to more cold startups which are slower. Therefore, we want to avoid memory wastage as well. Given these constraints, we want a garbage collector which supports us in being performant in these aspects. For instance, allocation happens very frequently during an app's execution. Therefore, we want fast allocations with minimal CPU consumption, thereby reducing battery drain. Then, to ensure that the GC doesn't cause janks, we want it to perform its activities concurrently, which means it shouldn't stop applications from making progress while it's doing its job of garbage collection. Finally, to keep a check on memory wastage, we want the GC to compact the heap so that fragmentation is taken care of. All these traits already exist in the Art's current garbage collector called concurrent copying. It supports fast bump pointer allocation and concurrently defragments the heap. But then the question is, why do we need a new GC? It's because in our current GC, these traits come at a fixed overhead for every object load. And it is incurred all the time, even when GC isn't running. This overhead is due to the fact that the collector uses something called a read barrier. It's a piece of GC code that is executed when an object is loaded by the application threads. To give you an example, here's a quick sample. In this case, the doSomething function, which is accessing objects B and C, would require running the read barriers under the hood on both of these lines. This overhead is both in terms of code size as well as execution time. Code size gets increased because the read barrier is inlined into the compiled code by the Art compiler for performance reasons. But this leads to higher demand on not just storage but also RAM and the hardware caches. And when it comes to the execution time, this barrier, which also contains a conditional branch, is executed every time an object is loaded. Furthermore, this cost is even higher when the GC is running, as the read barrier has to do more stuff than otherwise. In addition to the fixed overhead of the read barrier, there are some overheads that are incurred only when the GC is taking place. These are mainly due to the way the compaction algorithm works. In order to defragment the heap, it first copies all the scattered objects to another region contiguously, and then reclaims the space consumed by the scattered objects in the original region. Because of this, we observe what we call RSS cliff. RSS stands for resident set size, which is a metric of RAM consumed by a process. Anybody would expect that when a GC is taking place, over the course of the GC activity, RSS would at least not go up, if not down. However, in reality, since all the objects are to be defragmented, are first copied, and only in the end we are able to reclaim them, we first see a growth in RSS and then a sudden fall, like a cliff. This could potentially force the OS to kill background apps in order to alleviate the memory pressure, which otherwise could be a good candidate for hot or warm startup. Given these overheads in the current GC, it made sense to find a better alternative, if available. Fortunately, there is a Linux kernel feature called userfaultfd, which can perform the same functionality as the read barrier without its fixed overhead. So, we are developing a new garbage collector which uses userfaultfd for concurrent compaction. This new GC offers several benefits. The most significant one is that it gets rid of the read barrier. It turns out that on average, around 10% of the compiled code size was attributed to the read barrier alone. That in itself is a pretty remarkable improvement. But that's not all. There are some GC time benefits as well. With the new GC, we don't observe the RSS cliff because we are able to free the pages as the compaction progresses, rather than waiting till the end of collection. Also, there are several other ways in which this GC algorithm is more efficient than the current one. First, the number of atomic operations which stalls the processor pipeline and hence lesser the better are in the order of number of pages as compared to the current GC, in which case it's in the order of number of references. Reference count at any time on the heap is expected to be several orders of magnitude more than the number of pages. Second, this algorithm works sequentially in the memory order and therefore is very hardware prefetch friendly. Finally, this algorithm maintains the object's allocation locality. So the objects which are allocated next to each other by the application stays that way, thereby reducing burden on hardware resources. The ART performance story doesn't end with GC. Let's move to the other improvements in the runtime. Switching between Java and native code is much faster than before. We have seen up to 2.5x faster JNI calls with the new improvements. We have also reworked the reference processing implementation in the runtime. It has been made mostly non-blocking, alleviating the jank concerns that arise out of it. Also, we have made the refers to API public, which is recommended in certain cases over the get operation, as this helps in reclaiming unreachable objects sooner. For instance, in this code example, the get function is being used in a loop to just check if the reference has been nulled or not. In concurrent GCs, this could potentially keep the referred object alive forever, which is not intended by the developer. Using refers to instead addresses this problem and lets the object be garbage collected. We also made decent improvements to the class method lookup, which helped in making the interpreter faster. And finally, we now perform more bytecode verification, which checks the structure of the bytecode is well formed, at install time, so we can avoid ever doing it at the runtime. This is especially beneficial during app startup, where lots of code gets loaded and the VM needs to make sure it is all valid. To summarize, ART is lighter on the memory, faster on the CPU, and updatable on the device. And all the ART improvements that I talked about will arrive on every Android 12 device, irrespective of whether the user upgrades the Android release or not. Thanks for watching What's New in App Performance. Check out the performance samples to get started with benchmarking, jank stats, and baseline profiles. Make sure to check out the links below for more information on the topics we covered. Leave a comment, and if you like this video, use a thumbs up and subscribe for more.